Hi everybody, welcome to another video in pre-calculus section 4.6 logarithmic and exponential equation. So in this section we have logarithmic equation and then exponential equation. For logarithmic equation there are two types of equation. The first type where we have a number equal to a log, and in that case we can swap to exponential form. That is using the definition. The second type, when we have log on both sides, if the base are the same, the argument would be the same, so those are kind of cancel out. So two types, where we have log everywhere and where we have log on only one side. So those are the two types of the equation. But regardless of what type equation of the logarithmic equation we have, whatever we put in the argument of the log must be positive. So in this case, we must check the answer. We need to check the answer. Make sure that everything we put in every log must be positive. Right. Now look at the first equation. For log base 6 of x equal to log base 6 of 16. So what we see here is the log here and the log there. We don't have any constant by themselves. So in that case, we have to have one log on each side, and then the log we cancel out. So to do that, first we can take the 4 inside. So we have log base 6 of x to the 4th power equal to log base 6 of 16. Now both of them have log base of 6, so we can cancel them out. We have x to the 4th equal to 16. Now if we want to get back to x, we can take the 4th root on both sides. But just like when we take any even root, there should be a plus or minus. Where we take an even root on both sides. This is the 4th root of 16. So the 4th root, the calculator, if we hit math, go down to this option. So we can say the 4th root of 16. Of course, we can also say 16 to the 1/4, which is equivalent to it. Equivalent to the 4th root. So we have x equal to plus or minus 2. But note that we always have to check the answer. Right, at x equal to 2, I put 2 in for x. Note that we don't need to confirm that they are equal. All we need to check is that inside the log is positive. Actually, we need to put 2 here, right? Put 2 in for x. And whatever we put inside the log have to be positive. Yes, so in that case, it is a solution. Now check for one more. -2. Now this one is negative, so it doesn't work. Only positive argument for all the logs. Right. So easy, right? One log on each side, cancel out, the arguments must be the same. Right. Kind of like this one, we have 2 logs here and 1 log there, so we don't have any numbers by itself. So this will be the second type. We try to get 1 log on this side and 1 log on the other side, and then that will cancel out. So we see a plus here. So to combine the logs, so we condense the logs. A plus here turn into a multiplication. Now both of them have ln, which we cancel out. We have x times x minus 1 equal to x plus 15. Now multiply this out, x squared minus x plus 15. Move everything to the other side. We have a quadratic equation, x squared minus 2x minus 15 equal to 0. Here we can factor quadratic formula, but if it is simple enough, we can just factor. That will be x minus 5 and x plus 3. So a product equal to 0, one of the factor must be 0. So we have x minus 5 equal to 0, or x plus 3 equal to 0. So x equal to 5, or x equal to negative 3. Right? Now just like the last problem, every time we have the logarithmic equation, we need to check the answer, make sure that all the arguments are positive. When x equal to 5, I put 5 in for x, ln of 5 plus ln of 5 minus 1, ln of 5 plus 15. So this is positive, so it's good. Positive, yes, positive. Yeah, so we have all positive inside all the log, and so this is a solution. Next, I will check for x equal to negative 3. Put negative 3 in for x, and right on the first one it fails. So it's not going to be a solution. We don't need to write the rest of the equation. So that's what we have. Right. So just check the answer for all the log. Make sure that all the arguments are positive. Right. Right. Now, this is different than what we have earlier. This time we have a number by itself. So this is different type. Type 1, where we have a number by itself, in which case we swap that back to exponential form. If we have all the logs, try to get 1 on each side, so it will cancel. Right, so here we have a log and a number, so we need to combine the left hand side into one big log. That is subtract, so that will turn into a quotient. Right. This is by default is base 10. Common log base 10. Right. So we have a log equal to a number. We can swap into exponential form. Base is 10. 2 go to the other side. And x plus 4 over x go to the other side. Now we have 100 equal to x plus 4 over x over 1. Then we cross multiply. Let's continue over here. Cross multiply, we have 100 x equal to x plus 4. Move the x over, subtract the x on the other side. So 99x equal to 4. So x equal to 4 over 99. And now we check the answer. So log 4 over 99 plus 4 subtract log 4 over 99. Yeah, just substituting for x equal to 2. And here we have the positive inside log here, so that's good. This also positive, so that's also good. So x equal to 4 over 99 is a solution, is the solution. We only have one. Right, of course we can also check by saying log of 4 over 99 plus 4 subtract log of 4 over 99. We have 2, so that's good. Yeah. So if we have a number, try to get a log equal to a number and then swap to exponential form. Right. Same thing here. Now this is a sum, we will turn into a product. Log base 20 x plus 9 x plus 1 equal to 1. Now we swap to exponential form. 20 to the first power equal to x plus 9 times x plus 1 goes to the other side. Now multiply it out. X squared plus x plus 9x plus 9. Combine like terms, move the 20 over. Combine like terms, so we have 0 equal to x squared plus 10x minus 11 equal to 0. Right, look like we need to factor two things time together equal to 11. Not much option here, 1 and 11, and add up to 10. So that's easy. X squared plus 10x minus 11 equal to 0. The factor is x plus 11 and then x minus 1. Right. So when we multiply it out, that's negative 11, and when we combine that 10x. Right. So two things times together equal to 0. One of them must be 0. So if x equal to negative 11 or x equal to 1. Now we check the answer. So when x equal to negative 11, now put negative 11 in for x. This is negative, so this fails. This is not a solution. All the arguments must be positive, so that's not a solution. Now when x equal to 1, put 1 in for x. Now we check all the logs. This argument is positive, so that's good. That also positive, so that's good. So this is the solution. Right, so there are two types of logarithmic equation. The first type when we have log everywhere. So in that case, get one log on this side, the log cancel out. Now if we have the log and we have a number by itself, try to get a log and a number, and then swap to exponential form. and then either type of equation, we need to check the answer to make sure that all the arguments are positive. So that is the first part of the section, logarithmic equation. The second type of exponential is the second part of the section is exponential equation. Also have two types. The first types where we have different bases. So if we have two things with different bases, then we will switch to the logarithmic form. Now if they have the same basis, then the exponent will be the same, right? So if we can turn them into the same basis, do that, the exponent then will be equal. If we cannot do that, try to swap to this one, or take ln on both sides. Yeah. Which is equivalent to this. Right. So there are two types. Can we change to the same basis? If yes, do that. So the exponents will be the same. If we cannot do that, take ln on both sides, or we use that. Either way. Right. Now 4 and 8. 4 and 8, both of them we can write as the power of 2. So so 2 square and then 2 cube. Right, multiplying out 2x, then 3x minus 2. Yeah, power to another power. We multiply the exponents. Now we let the exponent equal each other. Bases are equal, the exponent will be equal. Multiply it out to x equal to 3x minus 6. Now minus 2x on both sides and plus 6. So if x equal to 6, 6 will be on the other side. Right. For exponential equation, we typically don't have to check. So that's good. If we can change both sides to the same basis, do that. So the bases cancel out, the exponents must be the same, because that is the one-to-one properties similar to the log. Right. Now let's assume that we don't see that, or we don't want to do it that way. There's always we can always take ln on both sides, even though we can change them to the same basis. So another way to do this is, by the way, is solution number 1. Here's solution 2. I can take ln on both sides. So we can take the x minus 2 and x outside. So we have x ln of 4, x minus 2, ln of 8. Here I can multiply it out. X ln of 4, x ln of 8 minus 2 ln of 8. Right. Now, since we solve for x, move that to the same side. And so we have x ln of 4 minus x ln of 8 equal to negative 2 ln of 8. Factor out of x ln of 4 minus ln of 8 equal to negative 2 ln of 8. And because we can divide that to the other side, so x equal to negative 2 ln of 8 ln of 4 minus ln of 8. And then you say, how do they equal? Actually, they do equal. So this is one solution. This is another solution. What I'm going to write next to show that they actually equal. So I will start from negative 2 ln of 8 and ln of 4 minus ln of 8. Right. So first, this is not a negative. Can you take the 2 inside? Right? So we have negative ln of a squared. Now ln of 4 minus ln of 8. When we subtract, meaning we divide the arguments. So we have negative ln of 64 over ln of 0.5 or 1/2. Right. Now, what's next? The 1/2. By the way, there's a lot of way to simplify this. ln of 1/2, can you write that as ln of 2 to negative 1, right? Because 1/2 is equal to 2 to negative 1. And I will take the negative 1 on the outside. So I will have negative ln of 64 over negative ln of 2. At least what we have here is cancel out the minus. We have ln of 64, which is ln of 2 to the 6. Negative cancel out, and then ln of 2. And then we'll take the 6 outside. There's a lot of way to do this, but what we have here is 6 ln of 2 over ln of 2. Cancel out, and it is equal to 6. So indeed, those two are equal. Or we can just use the calculator. Let's type that as a fraction. Negative 2 ln of 8 ln of 4 minus ln of 8 6. Right, so solution 1, solution 2, and indeed they are equal each other. Right, so two type of equation, and this is pretty much the two type. The first time we change them to the same basis. If we can do that, that works out a lot better. If we cannot, take ln on both sides. Right? Now, here, 7 times 2 to the x equal to 4. First we can divide by 7 on both sides. Try to get the exponent by itself. 2 to the x equal to 4 over 7. Now, one of them is base 2, the other one 4 over 7. The base is definitely not 2. So, of course 4 is 2 squared, but the 7 doesn't help. So what we do here is we take ln on both sides. And then we can take the exponent outside. So x ln of 2 equal ln of 4 over 7. And then divide by ln of 2, so we have x equal to ln of 4 over 7 over ln of 2, right? Yeah, this one we don't have another way to do this. Actually, we can also do it like this. Let's say 2x equal to 4 over 7. Of course, we can always swap to the exponential form. The base is 2, so we can write log base 2 4 over 7 equal to x. Yeah. So either here or here. By the way, they indeed are equal each other because from here to here, what we use is the chain of base formula on the previous section. They are equal. Right. So if we cannot change them to the same basis on both sides, then we take ln on both sides, or we swap to exponential form. We should get the same thing. But I usually just take ln on both sides. Right. The next one is a little bit different. We have 9x, 9 to the x power and 3 to the x power minus 12. The problem is the 12 here. So what we can do here is the 9, we have to try something here. 3 square is 9, right? Now here we can write is 3 to the 2x plus 3 to the x minus 12 equal to 0, right? Now what we see is I will write this as 3 to the x square, which is the same, right? Because that gives us 3 to the 2x. Now, what we see is if we let u equal to 3 to the x, we have a quadratic equation. So sometimes we have to do that. Let u be 3 to the x power. So that means u square is equal to 3 to the x square. So we have u square. So the equation becomes u square plus u minus 12 equal to 0. Right, so now we have equation in terms of u, which we'll solve for it first. Factor multiply equal to 12, so like 2 and 6 or 3 and 4. Certainly 3 and 4 will work. Plus 4 minus 3. So that is the factor, right? So we have u plus 4 equal to 0, or u minus 3 equal to 0. So u equal to minus 4, or u equal to 3. Right, so we solve for u. Now we can go back and solve for x. First, u equal to negative 4. U is 3 to the x. Right. We could go further, but we solve for x, different bases. Take ln on both sides, and the first step fails already because this one is undefined. Indeed, 3 to the x, remember, exponential function cannot be negative. So when it is equal to negative 4, it is no solution. You cannot have a positive number equal to a negative number. So we have no solution here for u equal to negative 4. Right, how about u equal to 3? Right, u is 3 to the x equal to 3. Now that one is easy, don't have to do anything. By default, 3 to the first power is itself. So in this case, x equal to 1. And that is the solution. We can check easily. 9 to the first power is 9. 3 to the first power is 3. 9 plus 3 minus 12 is 0. So that check. So I have x equal to 1. Right. So sometimes when we have two terms like this, we might have to switch to the quadratic equation. Right. Now we have some application problem. Suppose on January 1st, 2000, the population of Texas was 20.8. January 1st, 2010, it was 25.1. Estimate the population of Texas on 2030. In the context, the census is done every 10 years. And so we have 2000, 2010, and of course it might not be on the first day, but the census is done every 10 years, so we should have the numbers for 2000, 2010, and 2020. But here we estimate the population at 2030. Right, so we make a table. By the way, we will use this model, population model. Right, just draw a little table here. Right. So we have 2000, 2010, and 2030. Right. Say we have year, and then t, and the function p equal to p naught e to the rt. Right. Let's say in year 2000, to simplify the calculation, let's say in 2000 t is equal to 0. It makes things easier for the calculation. In 2010 will be 10 years later, and 2030, 30 years later. Now, the population here is 20.8 millions, 25.1 millions in 2010, and we don't know the population in 2030. Right, so that we set of data. First, 0 and 20.8. So we say at t equal to 0, the population is equal to 20.8. So we write, put 0 in, and we make that equal to p. So 20.8 equal to population initial, we don't know, p naught, but we know we know t is equal to 0. Now e to 0 power is 1, right? So here we have 20.8 equal to p naught. So we know p naught initial population is 20.8. So that's the first part of the problem. Next, go to second part of the equation. Ten years later, 10 years after 2000, the population is 25.1. Right, now we put everything we know in this equation. 25.1 for p equal to p naught 20.8 e to the r, t is 10. Right, now we will need to get the e to the 10r by itself, the exponent term. So I will divide by 20.8 on both sides. Right. Yeah, we just say 25.1 over 20.8 equal to e to the 10r. Now, we have the exponential term equal to that. Because this we cannot change to the same base. If we cannot change them to the same basis, take ln on both sides. Yeah, here I can just say multiply 10 top and bottom, or move the decimal place 1 to the right. We have 251 over 208, and that equal to e to the 10r. Remember, when we have e and ln and e cancel out, but first of course we can just take the 10r, move it outside, and then cancel the ln e. So ln of 251 over 208 equal to 10r ln of e, and ln of e is equal to 1. So in that case, we solve for r is equal to ln of 251 over 208 divided by 10. So let's just get the approximation here. ln of 251 divided by 208 divided by 10. So I have that. So actually, which means that the population increased by about 0.18%. Look reasonable. Even though I write like that, but when I do the calculation, I use the exact number. Will not round up anything. And finally, we go to the last part of the question. What happened to the population 30 years later? When t equal to 30, what is the population? So that's easy. Now we know everything about the equation. So the population is equal to P naught, we know is 20.8. E R is going to be this number. I'm just going to write 0.01879, and then T is 30. So I will use the whole number. I'm not going to use the rounding numbers here. 20.8 times, or just exponent natural base e to the, I just copy that number, hit enter, so that copy and paste, and then times 30, and we have 36.55, and originally it was million, so look reasonable. So the population estimate in 2030 is about 36.55 million. Right. So that is the population model. Right. Now we have a different model. This is called the Newton laws of cooling. So what we have is, let T be the temperature at the time T. So this is a function T. S is the surrounding temperature, so S is a constant. T naught is the initial temperature, which is also a constant. So here we have the constant S, and then T naught is also the constant initial temperature. So only T is a function. Surrounding temperature is a constant. Assume that to be constant. Otherwise it will be very messy. And T naught is also a constant initial temperature. So here is scenarios. So let's say we have the room temperature, whatever it is. If we have a very hot cup of coffee, original, let's say about 200 degrees Fahrenheit, if we set that in a room, then the temperature at the function of time will be given by this equation. The surrounding temperature, which is the room temperature, initial temperature of the cup of coffee, 200, minus the surrounding, and then we have e to negative kt. So that model will work. Now we have different scenarios here. Is suppose that we discover a dead body in a warehouse. The constant temperature is 82 degrees. Now we assume that the warehouse is at 82 degrees. Otherwise, if the temperature changing, that would be very difficult to use this formula. Now the body temperature recorded at 11 p.m. at 90 degrees Fahrenheit and 87 degrees Fahrenheit at 12:30 a.m. Estimate the time of death. Assume that the normal person is 98.6 degrees Fahrenheit. So obviously, if we are alive, then the blood flowing and then flowing, and then the temperature is constant 98.7. When we die, the temperature will cool off and will turn. After a while, the temperature should go down to 82. with the same as the room temperature, because that body will not burn any energy to generate any heat, so the temperature will slowly go down to 82. So the problem here is, of course, we try to draw the table just like what we have before, a little bit different. Right. Of course, the formulas that we can use time in hours or in minutes, but I will use hours because it's more convenient. So there will be 3 different states. So let's say the time in T, and then here's the T is the temperature equal to the surrounding. What is the surrounding temperature? The warehouse, 82 degrees. I just write S plus T naught minus S e to negative KT. Right. First of all, a normal person, just when he died, that person died, is 98.6 degree. So we can have 98.6 degree. That is where we die, and we don't know the time. We know that it is 90 degrees Fahrenheit at 11 p.m. But wait, for the simplicity, let that T to be 0. So we say 11 p.m. is 0. In that case, 12:30 a.m. is going to be 1.5 hours later. Right? So we can use hours, so we can say 1.5. And that will be 87 degrees. So that is what information we have. The time of death, don't know, but the temperature is 98.6 degrees Fahrenheit. 11 p.m. let that be 0. The time at that point is 0. Even though the concept of time being negative physically does not make sense, but in this model we can let time to be negative, meaning that the time before 11 p.m. not necessarily being negative time. And then 87 degree will be 1.5 hours after 11 p.m. Right, so that's what we have. Now, of course, from here we just pick out the pair of information that we know, and then choose the one that we don't, and then solve for what. Alright, so we will look at the last one. Do that last. What we do first is look for something easy. So let's look at this pair of data. By the way, we do know the surrounding temperature, 82 degrees. Right, we don't know the initial temperature. Actually, the initial temperature is 98.6. We know that, but worry about that later. Now focus here. When T equal to 0, the temperature is 90 degrees. Just put 90, just drop the unit. So now let's put on the information we know. 90 degrees equal to the surrounding 82 plus initial temperature we don't know, the surrounding temperature we do know, and e to negative k, don't know k, but we know t, we let equal to 0. Right, so here we can simplify, subtract 82 on the other side. 90 minus 82 90 minus 82 is 80, equal to T naught minus 82 e to 0 power, right? K times 0 is 0. So e to 0 power is 1. So we have T naught minus 82 is equal to 80. Right, so 8 equal to, this is times 1, so T naught minus 82 plus 32, 82 on the other side. So initial temperature is 90. So there's a reason we write this is T naught, meaning that the temperature when T equal to 0, right? So we have T naught equal to 90, which is good. So first set of data, that's what we have. Now let's go to the second set of data. We will go there last because we don't know that. Here we do know at T equal to 1.5, the temperature is equal to 87 degrees. Now that is this is the equation. I put 87 in for T. And S, surrounding temperature 82, plus T naught, we do know now the initial temperature is 90 degrees. Minus the surrounding 82, e to negative K. Now we know T now is 1.5. Right, now subtract 82 on the other side. And this gives us 8. So we have 5 equal to, that cancel out, 8, 90 minus 82, e to negative 1.5 K. Right, now to get the exponent by itself, I divide by 8 on both sides. 5 over 8, that should be a decimal. .625. Now, to solve for K, there's no way we can change this to the power of E. So we take the ln on both sides. Right. Now this we can take the exponent outside. ln of 0.625 equal to, take that, negative 1.5 K ln of E. Ln of E is equal to 1. So we just divide negative 1.5 on the other side, we have K. I just get an approximation. ln of 0.625 divided by negative 1.5. So the rate here is 0.31336. So that's the second data point we saw for the rate K. And finally, we substitute back into the last part of it. What is the time when the temperature is 98.6? So time equal to what? Where the temperature is 98.6. So we have 98.6 equal to surrounding temperature is 82 plus initial temperature is 90 minus 82 e to the negative kt, negative, this is k, just going to put that for now. When we do the calculation we use the whole number. Subtract 82 on the other side. 98.6 minus 82. We have 16.6. And 90 minus 82, that is 8. E2 that. Right, to get the exponent by itself, we divide by 8. 16.6 divided by 8 should be an even, a finite decimal, 2.075. And 8 cancel, we have e to the negative 0.31336 t. Right, similar to the last one, we take ln on both sides because exponential equation where we cannot convert them to the same basis. There are 3 threes. Right. And take the exponent outside. Yet the routine is exactly like what we did earlier, except this time we solve for t instead of k. And we take that outside. ln of a is equal to 1. So divide that to the other side, we have t is ln of 2.075 divided by 0.313336. Right, so we take ln of this number divide by that number, and there's a negative in front of that. We have negative 2.3296 something, and the unit is in hours. So if we want to convert this, click second, application, convert to degree minutes, second. So we have 2 hours, 19 minutes, and 46 seconds. Hour 19 minutes and 47 seconds. Usually just an estimation, so we choose around 2 minutes would be very good already. I'll go way back to what we have from the beginning, right? So we have 2 hours and 19 minutes. So when t equal to 0, we have 11 p.m. So we have 11 p.m. Now we subtract, which is 2 hours and 19 minutes before that. So the person dies 2 hours and 19 minutes before 11 p.m. so we cannot subtract here 0 0, so we borrow 1, so make this 60. So 60 minus 19 is 41, and then 10 minus 2 is 8. So that is the estimated time of death. Of course, we can ignore the second. Right. So bottom line is we just have one equation at different state. Of course, here we can use differently. We can say, let's say the time of death is 0, and then the 11 p.m. is x times later. So, and then after that 12:30 is going to be x plus 1.5. Yeah, of course we can write like that too, but setting up like this is easier. So you have 3 different states, 3 different temperature. And so just put all the numbers we know in, and in that case we solve for T naught because temperature is equal to 0, so e to 0 power is 1, and we have T naught, which is the temperature at 0. Those should be 90 degrees. That should be 90 degrees. So yes, it is. Right, and then we use second data point, 1.5 hour later, the temperature is 87 degrees. So 87 degrees, surrounding 82, initial is 90, surrounding 82. So we do that, we solve for the rate K, and finally we put it back into the equation, and we solve for T, and T turned out to be negative 2.32, which will convert to is 2 hours and 19 minutes. Right? If we have this, subtract 2 hours, and then we multiply by, this subtract 2, I should, of course that's wrong. If we just take the decimal, I mean we should add 2. If we just want a decimal, times 60, so that's about 19 minutes and something. So just approximation. So that should be 20 minutes. If we round that up to 20 minutes, so the time of death is 8:40 p.m. Right. So yeah, I thought that is a nice application problem. So bottom line is when we solve the exponential equation where we cannot change them to the same basis, take L1 on both sides. We do that the same on both of these parts. Right. Anyway, I stop that section, this section here. As always, thank you for watching, and see you in another video in pre-calculus.